My name is Lydia Maisie. I work in international engineering operations, and I'm responsible for setting up offices around the world for Google engineering offices. So I came across these guys a year ago while attending an emerging technology forum for Russian and Ukrainian startups. And we had this idea to bring them in here and present it to you guys, the technologies that they're working on. So Jim Nickerson is an interim CEO. He has many years of experience, I think 20 plus years of experience in ultra-capacitors industry, or high-tech industry, and maybe most recently in ultra-capacitors. And I think last 2 years he spent at Maxwell Technologies. And then Vladimir and Sergey will be available for questions. They're investors in the company. So with this, I'm going to hand it off to Jim.
Thank you, Lydia. We'll just turn this one off, I think. And
right, you have your own.
They gave me my own. Well, good afternoon. My name is Jim Nickerson. As Lydia mentioned, I've been in the technology industry for more than 20 years. Much of my career was here in the Valley. I was in the semiconductor industry working for National Semiconductor and XR and others. But about 10 years ago, I was introduced to the technology called ultracapacitor. I'm not sure if you've been keeping up with that. This talk is described as energy crisis management using a new technology to enable some of the current alternative energy options that are being bandied about. To call it a new technology is a little bit of a misnomer, because the first ultracapacitor, if you go back to a Radio Shack self-help guide that they published in 1967, they showed how to build an ultracapacitor using paper towels and lemon juice. So the technology, the idea of a double layer capacitor has been around a long time. It's just been trying to get that technology to a point where it's actually usable by other industries other than people that read Radio Shack publications. So the problem that the ultracapacitor is trying to address is the fact that as we have watched the global energy crisis develop, one of the things that's come out of that is the idea that we need to find more efficient ways to use the energy that we have, whether it be oil or solar or wind power. We need to be able to most efficiently use that energy as it's generated. So this technology of ultracapacitors is designed to help enable that type of technology by providing a high power burst capability, to provide fast charging and discharging type technologies, and then also to enable peak load leveling. One of the biggest problems in the energy industry is how do you generate power, for example, solar power. It's easy to get power during the day, but at night it's pretty difficult. So the ultracapacitor is a technology that on a smaller scale, and even to some extent on that scale, enables you to balance your power and energy so that you can deliver power at times when it may not be most efficiently available. So if you look at the common technologies, you'll see conventional batteries in the big yellow galaxy up there. And you can see that looking at that, if the left-hand axis is energy density, the bottom axis is power density. So how much energy can you store versus how much power can you deliver? Conventional batteries reside up there in that yellow galaxy. Fuel cells, as they're being developed, are up even further up in the left-hand corner. A conventional capacitor, which discharges very quickly, can give you a lot of power, but very quickly. So it doesn't have much energy storage capacity. So the ultracapacitor, the red galaxy there, lies in the midst of all that as a technology that'll help you bridge from one application to another. Many applications use batteries, many use conventional capacitors, but those are oftentimes sized for the opposite axis. For example, you may, if you need a lot of energy capacity, but you have a capacitor type power delivery requirement, you may have to use too large a capacitor for your application just to hold the energy you need. Or you may have to oversize your battery because you need to deliver more power than you want to. So this is kind of the universe that we're talking about. Comparing them side by side, I won't go through all this in great detail, but if you look at a battery, an ultracapacitor, and a capacitor, you can see that there's orders of magnitudes of difference in the two columns. Some of the critical ones are the cycle life, where a battery can be charged and recharged on the order of thousands of times. Ultracapacitors are in the hundreds of thousands of times, primarily because a battery is a chemical device and an ultracapacitor is a mechanical device. It's just moving ions and pushing them back and forth, so there's no breakdown of a chemical. The efficiency of charging and discharging, in other words, if you charge it and discharge it, how much efficiency can you get in that cycle? The ultracapacitor and the standard capacitor are much higher than what you can get out of a battery. Now, there are some new battery technologies, lithium-ion technologies, that are very expensive, that are pushing up the top end of that 85% for batteries. But you still have to keep in mind that most of these applications are cost-driven, so you have to keep that in mind. The other thing is, because of that, the mechanics of charging, a battery typically takes hours to charge, where an ultracapacitor takes seconds, and a capacitor you can do almost instantaneously. And another nice feature for the ultracapacitor is you can operate at much lower temperatures. So if you're in a car that's having a hard time starting with a battery, you could easily start it with an ultracapacitor if you're living in Minnesota. This is a kind of a model of how an ultracapacitor works. It's much like a battery. You have a positive and negative electrode. You have charged ions in the electrolyte. When you close the switch, they go to the opposite poles, and they're stored there. The important part is this is the electrode. The important part is how many of these ions can you store in the electrode. So where a battery might have a plate there, and the charge is stored on the flat surface of a plate, an ultracapacitor has almost like foam or a sponge. So there's all sorts of nooks and crannies, so you can store much more, you can put many more ions in against the electrode, hence the higher ability to store energy. This is an equivalent circuit, and all that's meant to show you is that in an ultracapacitor, because you've driven those ions into this three-dimensional electrode, it takes a little bit to pull out of it. So you have some internal resistance to pulling that out. So you need to think of an ultracapacitor as being capacitors and resistors in series. When you build an ultracapacitor, you have two current collectors, electrolyte. Your electrode is your porous, normally carbon-type material that you see there is the yellow circles. And then the electrolyte is what is immersing the whole thing. There's a separator between the two, so the separator is what's keeping your positive and negative apart once you've started charging it. Now, one of the things that you have to keep in mind is that this electrode material is very dense, and this is would normally in other industries be called a starved cell, in that there's so little electrolyte in there that if you punch a hole in it, nothing will drip out. It's so starved. So what are the major applications for using an ultracapacitor? If you think of an application's use of power, many types of applications, and I'll use an old one, but we were talking today that it's a little outmoded because BlackBerry has gone well beyond that. But their original two-way pager, the Motorola two-way pager, you would have a constant requirement for power, and then you'd press the button, and all of a sudden you'd get a burst of power requirement to do a transmit. And then it'd wait for a little bit, and then you'd burst again. There's many types of applications that you could apply to this. You could apply this to a car. Car's traveling along, all of a sudden you need to accelerate, you step on the gas, and you need a burst of power. So this is just kind of a generic description of what an application might look like. And normally that application has some constant power supply. A battery, an engine, a fuel cell, just about anything that's applying purposely a standard level of power. And you have to size the power so that it's always above your minimum requirement, the bottom red line there. And you want to try to accommodate your burst requirements. So maybe in reality, 80% of the bursts of power required in this application might actually come in below the black line. But it's the occasional one that goes above that is really going to damage your energy supply. So what the ultracapacitor does, when you put that together with this system, is the ultracapacitor stands by and fills those gaps whenever it's required. Now, it may not seem intuitive, but if the black line is a battery has a resistance to delivering power. So you just can't say, give me X number of watts immediately, because the battery has resistance and it resists discharging that power. You've probably seen that in many types of applications. The ultracapacitor, because its resistance is so much lower than a battery, when put in parallel with the battery, that load sucks the energy out of the ultracapacitor rather than the battery. So the battery goes along and doesn't even know it happened because the ultracapacitor took care of it. And we'll talk about that effect a little later. Now there's the opposite side of this spectrum. What if your power requirement is constant? What if you're a hospital? What if you're any type of computer system or RAID backup type system, etc.? We all know that the power company is not very good at giving us very clean power. Now, on this scale, these dips might be milliseconds rather than seconds or minutes, or it could be a brownout type of situation. So in this case, you size your application is sized right at your constant power, but if the power drops off, once again, the ultracapacitor will discharge to fill in that sag in the available power. So in this is a type of case where you would have a power requirement and the incoming power for some reason crackles or dips or goes through some sort of disruption, and you can't afford to have that happen, so you have an ultracapacitor in line with that power, and when it sees all of a sudden that the power has gone away, it discharges, so it fills those gaps. So this type of technology can then be applied to a wide variety of applications. It can be applied to consumer electronics, where you have something like a digital camera that when you flash, when you take the picture, you have a surge of power because it needs to write all those bits all of a sudden. Normally, it's just sitting there keeping the display open. You have applications like wind power, solar power, and even standard hydroelectric power plants or coal-fired power plants, where you need to temporarily store energy in order to be able to deliver it in a smooth way. They would like to be on the opposite end of that last slide, where they get paid more for cleaner energy delivery. So if they have factories that have critical processes in their path, they want to make sure that they deliver the cleanest power that they can without any dips or jumps. So they would like to put ultracapacitors right outside their door so that as they're feeding power out, they can take care of those ups and downs themselves. They charge more for cleaner power. So for them, it's an economic incentive. If we look at the global market, it's growing. The technology has been around for a long time, but people have had a hard time implementing it in a way that is cost effective and will let these applications take good advantage of it. This year, you'll see basically this kind of a breakdown between consumer, industrial, and automotive or transportation type applications, and we'll describe those a little better. But it's going to be growing significantly, and you'll see that what's forecasted to grow the most is the automotive or transportation side. With the advent of electric vehicles, hybrid electric vehicles, when I first got involved 10 years ago with ultracapacitors, we were talking about electric vehicles and how ultracapacitors help them. As we went through the next 5 years and the hybrids started becoming more of what the automotive world wanted to go to, we got more excited because hybrids use ultracapacitors even better than electric vehicles do. So as the market develops, the only thing holding it back is it too costly to implement. On the consumer electronic side, we've talked about some of these types of applications and where the ultracapacitor is really pumping power into the application, either to, on a small level, balance the power requirements, do the power balancing. But one of the major things to take note of here is that the ultracapacitor, because it can be cycled so many times, it has the ability to be recharged almost at will. So if you have a burst power application that might be sending a transmit to a GSM satellite, for the Air Force has emergency radios that send a 1-second burst to their satellite every minute. So if you have a long 1-second burst, but then it's quiet for 59 seconds, if you put a battery in next to it, you can get the ultracapacitor to provide that burst, and then the battery just kind of trickle charges the ultracapacitor back up to capacity. Over the next 59 seconds, it's ready to go, and boom, off you go. The battery never gets degraded because it's having those high power requirements pressed on it. So it's an application, that's an example of how the ultracapacitor put in parallel with the batteries, even the little C cell, D cell type batteries, if there's a burst requirement, we've demonstrated on cell phones and toys and other applications that you can extend the life of the battery by up to 4 times, solely on the basis of the fact that the battery is not seeing those high power requirements and having to charge and discharge. I mean, all battery chemistries are going to degrade over time, and that's why you have limited cycle life on a battery, is because it's constantly degrading that chemical reaction that's building the energy that you're trying to discharge in the form of power. So on a smaller scale, there's many applications in the consumer electronics world. We talked about industrial power management. Once again, this is a case where the power companies see a big advantage. I've spent several trips, gone out into the fields of Utah, where you have power grids that are stretching for miles, and there's nothing in between the two relay sites for either power or telecommunications sites. And you get out there, and there's this shed that's probably 20 by 20 by 10 feet tall, and it's full of lead-acid batteries. And those batteries are sitting there so that if there is a drop on the power grid that could potentially start cascading, they need to hold it up as long as they can, normally, so that they can start a generator to start feeding power back into the grid. So if this stack of lead-acid batteries, hundreds of lead-acid batteries, start leaking, or they have bad batteries in the middle of the stack or whatever, the power companies and the telecommunication companies spend ungodly amounts of money with people traveling around in trucks doing nothing but maintaining those stacks of batteries. And they're expensive, and they're ecologically hazardous, having all that lead out there. And they leak all the time. In the case of the power grid, what we did was we set up a fuel cell next to an ultracapacitor, put it on the grid. We just took right off of the power lines, we just trickle charged the ultracapacitor so that it always maintained its full charge. And the total box of ultracapacitors is about the size of this table here. So we had a box of ultracapacitors being constantly held at full charge just by trickle charging off the power line. Put a fuel cell next to it. Now the fuel cell, because a fuel cell generates power based on generally pressure of hydrogen or whatever you're using in the fuel cell, if the power goes away off the grid, all of a sudden there's no power available. So the batteries or the ultracapacitors would have to be there to start the fuel cell. Well, the ultracapacitor is great for delivering power for a couple of minutes, long enough to get the fuel cell pressurized to the point where it's delivering sufficient power that it can run. Now you have a set here of both a fuel cell and an ultracapacitor set that needs basically no maintenance activity, because the ultracapacitors will charge and discharge and be fine for 100 years and hundreds of thousands of cycles, and the fuel cell is pretty much inert until you fire it up and start pressurizing the hydrogen. So of course after you do that, you'd have to go out and refill your hydrogen tank, but that's about it. And the other major application is transportation. We've kind of focused on the automotive side of transportation here, but the automotive world includes things like forklifts and many other trucks, buses, etc. The ability of the ultracapacitor to provide the burst power and do fast charging is really critical to making an HEV, a hybrid electric vehicle, successful. Because a hybrid electric vehicle needs, in order to sell these things, you have to have some performance. So you got to sell it to people that know when they step on the gas, it's going to jump and go forward. But you also want to capture the braking energy. In a hybrid electric vehicle or an electric vehicle, your wheels are electric motors, driven by electric motors. So when you go to slow down an electric vehicle, you don't apply brake pads and lose all that energy. You reverse the motor and you pull energy out of the wheel. So what you're doing there is you're charging the ultracapacitor. So braking a hybrid electric vehicle is charging the ultracapacitor. Now, if you've gotten down to the point where you've actually stopped, which is always a good idea, now it's time to reaccelerate. Well, you have a fully charged ultracapacitor sitting there with nothing to do but discharge and give you as much power as you need. So we went up to Los Angeles and put a 300-volt ultracapacitor system on the top of a city bus up in Los Angeles. Now this was a diesel hybrid, so it had a diesel engine, a small diesel engine, and electric motors in the wheels and batteries. We put ultracapacitors up on the roof of this thing, about 300 cells that were the size of Australian beer cans. And that, just doing that, by feeding the power through the ultracapacitors, we were able to demonstrate that, well, you've all seen a city bus come up to a bus stop and then try to leave. The first thing you get is this big black smoke cloud as the bus tries to get away from the curb. Well, because the ultracapacitor was there, it just discharged the ultracapacitor. So the diesel engine didn't even have to rev up. It just stayed in idle. The ultracapacitor provided enough power to push the bus away from the curb and get it up to about 20 miles an hour. At that point, the diesel engine just kind of came in on a smooth accelerate and accelerated and then took over driving the bus down to the next bus stop, where the ultracapacitor would be recharged and the whole cycle would repeat. Well, the efficiency of capturing that braking energy in a bus and feeding it back into the drivetrain lowered the emissions of that diesel hybrid, which already had a small diesel, by 60%. So it had a dramatic effect on how much fuel and how much emissions were going through that diesel engine. Now there's another part of the automotive world that seldom gets a whole lot of attention from the ultracapacitor guys, but it's very important. Most of the major automotive companies are now looking at putting in high voltage subsystems. Typically it's 42 volts. And that's because in your car, you have a 12-volt battery, or maybe a 16, depending on your car, but you have a 12-volt battery, and every time you roll up your power window or do your power locks or turn on your radio or do this, that, or the other thing, you are dragging down on that battery system. So the battery has got to deal with all of those extraneous power requirements going forward. The ultracapacitor, put in series with a small battery, 42-volt battery, allows you to reduce the current runs. You can do it with thinner cable, and you can power all the safety things independent of the car battery. So it becomes not only a more efficient use of power and energy inside the vehicle, it also adds to the safety, because if you have an accident and you disable the battery, you have backup power normally located close to where the thing is going to happen. So you have your window motor has the ultracapacitor right there. We saw a demonstration at Ford one time where recently somebody had driven their car into a lake for some reason, and they couldn't get their power window down because as soon as the front of the car got in the water, it started shorting out their electrical system. Their power window wouldn't go down. Well, the ultracapacitor sitting there right on the window motor, it doesn't matter. It immediately took the window down. In all the time I've spent with the automotive companies, there's probably 100 examples of how node power can provide a big advantage to an automobile. Here's an example of how the Honda electric vehicle uses an ultracapacitor. The motor power that you see there, that's the motor running. So those are the wheel motors in sum. So your ultracapacitor, when you accelerate the vehicle, because here's power going up and here's the acceleration curve. So as your speed is going up, the ultracapacitor is discharging to support the fuel cell as it comes up to its load. And so the two combined allow you to do a quick acceleration, and then you drive along, cruising along until you start to brake, and at that point you start shutting down your fuel cell, your speed starts dropping dramatically, but your ultracapacitor starts charging. So now your ultracapacitor is charging down in this area because it got depleted during this cycle. It was back down to 0 power. Now it's going to recharge and be back and ready to accelerate again. So I've talked about all these different applications, and why aren't these things out there in everything already? They should be. I mean, Radio Shack showed us how to do it 45 years ago. So the problem is that the issue becomes, how much is the cost of the delivered power from a specific energy density? Now, as I said early on, you can always deliver power, but from what energy source? So if you need to have really high peaks of power and you can't live without it, you need to size your battery large enough so that it will supply that power peak on demand. If you don't, you can't get that power out of the battery. Now, the other issues of the battery cycle life and everything and how much that hurts the battery are immaterial at this point. What we need to do is worry about, is the cost of putting the capacitor in there enough to offset the cost of the larger battery that you had to put in there, combined with the weight that you're carrying, the efficiencies, the miles per hour, or the miles per gallon, all the other economic reasons why you would want to worry about size, weight, and density. Also, the efficiency of the charge and discharge cycle. If you do it on, how often do you have to change your car battery? Maybe not that frequently anymore. They've improved that technology. But you have to, an ultracapacitor will go for hundreds and hundreds of thousands of cycles without being changed. So there's a lot of charge-discharge efficiency that's going to benefit the application. Now, it may not be so obvious in a car, but how often do you change the batteries in your pagers or other applications that are using burst power? I alluded earlier to the temperature range. Ultracapacitors, because of their starved electrolyte, will operate down in the -55 level even. The military, both in Russia and in the United States, has for several years been looking at ultracapacitors, testing ultracapacitors as emergency start, cold weather starting. So you just throw it into the battery box of a diesel truck, and when it's too cold for the battery to start the truck, you just flip over and start it with the ultracapacitor, and off you go. By the time the truck warms up, the battery warms up, everything's fine. Then you recharge the ultracapacitor. Total cycle life, and then safety. Safety, as you're pulling energy out of a battery, you're stressing it chemically, so it warms up. You get very hot batteries when you have a lot of power requirements on them. The ultracapacitor will allow you to lower the overall system temperature simply because the ultracapacitor generates no heat when it's discharging. So APCT, the company that we're working with, what we have tried to do and what's been developed by this team based in Kiev is a new implementation of the ultracapacitor technology where we can achieve a higher power density, the ability to deliver those peak powers, based on modifying the current collector that, if you recall in that earlier diagram, we modify the current collector in a way that reduces the resistance of the current going through. So it makes it a much more efficient power delivery device. The same team has also devised a nanoporous electrode, which is a carbon electrode that they can precisely determine the size of the pores in there, make them fit the ions that are being pushed in and out. So they can optimize the amount of energy that that electrode can store. So the two together means that you can deliver more power than competing ultracapacitor technologies, and you can store more energy than competing ultracapacitor technologies. And then again, the low internal resistance helps with keeping the overheating issue under control. If you look at ultracapacitors that are being delivered around the world, there's two types of ultracapacitors. Some are normally called supercapacitors, and those are delivered by companies like Panasonic. A lot of the Japanese consumer electronics companies have small supercapacitors. Now, they are very inefficient in the terms of their power density. They're very cheap to make and very easy to make, but they have no power or energy density capability to speak of. So they do work in certain applications. You'll find one in everybody's VCR. You know, I remember when years not too long ago, you know, if you had a brownout in your house, you had to go around and reset all your clocks, reset your VCR, you know, reset everything that didn't have a battery backup in it. And now they put these little cheap supercapacitors into a VCR. So if you have a glitch in power, it'll ride through that power glitch for as many as 10 or 20 seconds. But beyond that, it's depleted, and you'll have to go fix the clock when the power comes back. But you can ride through changing out the batteries. I'm always looking for ultracapacitors. I found when I installed an automatic thermostat in my house that had a couple batteries in it, when it gave me the low battery signal and I pulled the batteries out, I was going to lose all my programming. But there was an ultracapacitor in there, and if it weren't for the fact that I would habitually drop the batteries and not find the new ones fast enough, I could have changed the batteries without losing the programming. The APCT technology, if you look at this, the ultracapacitor mass is on the left hand, and the power delivered to a load in kilowatts is on the bottom axis. The APCT versus the current high power ultracapacitors, like those made by Maxwell Technologies, the APCT prototypes deliver at the high end here at about 1/4 of the mass. And in the case of ultracapacitors, 1/4 of the mass is 1/4 of the size, is 1/4 of the cost, in very general sense. The further down you get, the more packaging becomes part of the issue, so you lose some of that advantage the further down you get. But on the high end, where you're looking at automotive and industrial in particular, that significant difference translates into a much better cost structure than is currently available. Right now, to get a 1 kilowatt ultracapacitor on the current marketplace, that the price is a little over $300 and coming down slowly. When I was at Maxwell Technologies 6-7 years ago, I was selling a 1 kilowatt device for $2,500, the size of an Australian beer can. Now it's gotten down to the $300 range, but you need about 100 of them to make a hybrid electric vehicle work. So 100 times $300 isn't very conducive to hybrid electric vehicles. If you come down and look at this yellow one, that's the APCT cost to manufacture, the same 1 kilowatt. So you can see that we've really broken under the $50 per 1 kilowatt module range and have the opportunity to keep going down. So what we're doing is making a major jump in the cost structure of the technology that we hope will allow all these applications that are taking advantage of new energy alternatives to become more successful and more efficient. APCT, the company that's doing it, is a US registered company formed by a group of Ukrainian scientists in Kiev. Over 50 man-years of experience. I've worked with parts of this team over the last 10 years. The seed investment came from Tech Invest, a VC firm based in Kiev. And we're working on how to get this to market in the most effective ways. And we're looking at joining and doing strategic partnerships with some US and Asian-based companies that are into manufacturing batteries and ultracapacitors, and also developing our own manufacturing capabilities both in the Ukraine and in the US. And some of the testing that's been done, Dr. Andy Burke out at UC Davis is one of the gurus that I've known for 20 years that does all the analysis, and he's in fact getting ready to do a presentation in Florida next month that will show APCT's technology compared against the other competitors. So that's our presentation. We're happy to take any questions. These are the two locations, one in Virginia and the main office in Ukraine. I'm out of San Diego, and I'm working with this team to see how we can develop the US marketplace and get it rolling. We'd be happy to take any questions, and the team from APCT is here to answer technical questions, and we're open to any of your ideas or suggestions. Yeah.
Say I'm trying to get rid of a lead acid battery, 10 amp hour at 14 volts. What would be the size and cost of something like that if I just went to all ultracapacitor?
Well, the first problem you're going to run into is getting rid of it because it's got lead in it. So, yeah, but you have to recycle it. I don't know that I can size the ultracapacitor. 10 amps, 10 amp hours. You know, I can't answer that question off the top of my head, but why don't you see me afterwards and we can sit down with a pencil and pencil it out.
Is there some standard size that I could get a handle on? I don't have a feel for size and cost.
Well, a standard, one of the larger cells made by almost all the manufacturers right now is roughly a 2,500 farad ultracapacitor. A 2,500 farad ultracapacitor is roughly 1 kilowatt of delivered power. And it can be delivered over different lengths of time. If we go back to, let me see if I can go back to that. So on this slide, what you see, and a lead acid battery generally falls within that battery complex. The power delivery is basically watts, and the energy is watt hours. So if you were to, what we'd have to do is calculate the watt hours and the delivery capability, and by going through the math from your amps to create the size that you would need. Yeah.
I had a question about, I know with batteries you have to worry about thermal runaway and things like that. What are some of the concerns about ultracapacitors, and how do they stand up to crush testing and things like that?
Ultracapacitors have been tested pretty dramatically. Because you're really only moving ions back and forth, you don't have that any chemical reaction going on. So you really don't have any internally generated heat in an ultracapacitor. Now, historically, the ultracapacitors being made by Maxwell and others have used acetyl-nitrile as being the electrolyte in that cell. And that acetyl-nitrile includes, now the word slips my mind, what's the poison? A poisonous substance. So you don't want to get it on you. We always made the argument that the way you would, I can't remember the word now, the way you would clean up a spill would be with carbon cloth, and we had the carbon cloth built into the ultracapacitor. But because it's a starved cell, there's no physical, the only physical reaction to being crushed would be the potential to leak electrolyte. Because there's no chemical reaction going on, there's no danger of explosion or anything like that. The failure mechanism for most ultracapacitors that have been tested by a variety of companies is that they slowly leak. They'll develop a pinhole leak, and they'll get salt forming on the outside of the cell. Honda, when I was working with Maxwell, we had a joint development agreement with Honda the Honda HEV and the Honda electric vehicle and the Toyota Prius are the major production vehicles that have ultracapacitors at this point. And in testing, they were driving nails through the ultracapacitor cells just to see what would happen. So it's proved to be a very safe technology in automotive applications and other smaller applications. Yes?
So how long do they hold the charge? I mean, they talk about sort of using the battery replacements.
We did some tests with Disney because they wanted to put ultracapacitors into their parking lot trams, and determined that a good ultracapacitor will hold its charge above 90% for 72 hours or longer. They do tend to, they will leak. I mean, those ions will slowly start coming out of the electrode. However, you can charge it back up almost instantaneously. So one of the requirements, or in most applications, you'll often see a recharging capability fairly close. I don't know if APCT has demonstrated any charge holding testing recently, but generally you can hold it above 90% charge for at least 72 hours. They'll fully discharge over, depending on the manufacturer, several weeks. So it's not an energy storage device for long-term storage. Yes.
What is the limiting factor for energy density, and what is the trajectory for energy density over time for, say, the last 10 years and going forward?
The limiting factor on energy density is how much of that ion can you put into the electrode. So it's become a real science to determine, if you picture the electrode as being like a sponge, the electrolyte is flowing through here, and as you charge it, those ions are working their way into this sponge because they need as much surface area as possible. So the energy density is the total surface area that's available when you charge it. So as many ions as you can put up against the electrode. If you imagine a flat plate electrode, you've got a flat surface. In 2 dimensions, you put as many ions on there as you can. With an ultracapacitor electrode, a 3-dimensional surface, you cram as many of them in there as you can. You have the problem that if they have to go in too far, if they tunnel in way in there, then they're going to be encountering and creating resistance in getting out when you discharge it. So you have to balance the total surface of the electrode, which is your energy density factor, by your desire to deliver power, which is the resistance to getting them out of that. So that's one of the things that you do, with ultracapacitors, is you balance what you want in terms of energy density against what you want to deliver as power. So it's, and they've made some pretty good strides over the last 10 years. I mean, it's gone from, APCT has demonstrated a dramatic new ability to deliver power by having this nanoporous electrode and this etched specialized current collector that, when combined together, both reduce the internal resistance and provide more surface area. So you're dramatically increasing your energy density and lowering your resistance at the same time.
Can you quantify that? It seems like the ultracapacitors maybe still an order of magnitude short of where it would want to be in terms of replacing batteries and applications.
Okay, one of the things that the one thing that an ultracapacitor will never do is replace a battery.
Largely replace the battery. You might have a significantly smaller battery and a larger ultracapacitor.
Right. That becomes a matter of cost. From a technology standpoint, it's been demonstrated over and over again that you can reduce the volume of battery by a factor of 4 in some applications that have high peak power requirements. But it costs you 10 times the cost of the batteries. So you could be replacing batteries for 50 years before you pay back the ultracapacitor. So it ends up being a cost issue. The technology has been there. It's just a matter of, can you build it and have it reliably deliver the power you need in that application? And also, can you make it small enough physically to fit that application? So all the applications, and I come from a marketing background, so I look at the ultracapacitor as being only a tool to solve an application problem. So if the application can be solved with the ultracapacitor, if it took an ultracapacitor as big as this table to make a two-way pager work well, and make it so you never had to change the alkaline battery in a two-way pager, okay, that's the starting point. Now let's get this ultracapacitor down in size by improving the energy density and the power delivery capability. Let's get that ultracapacitor down in size and cost to make it realistically go into that two-way pager. So much of that has been done except for the size and cost aspect. You're right, it has another order of magnitude to go, and that's what APCT is trying to demonstrate now with its prototypes, is that they have made that order of magnitude jump, almost an order of magnitude jump, 4x the power in a given volume. So the APC ultracapacitor is positioned to be one that could enable many of these applications. Not because it's more powerful, more dense, has higher energy density, but because it can do the same power delivery in 1/4 of the volume. It takes 1/4 of the material. It takes roughly 1/4 of the cost. So the real application requirement has been met with something that's 1/4 of the size and roughly 1/4 of the cost. So it enables then that application to go forward. Automotive hybrid electric vehicles, as I mentioned, need about 300 volts worth of cells. Ultracapacitors, I actually never made it into this presentation, but an ultracapacitor is like a battery, and then it's pretty much limited at 2.7 volts per cell or so. So you need to put about 100 into a car to make it work. So right now, the hybrid electric vehicle wants that battery pack to be about 1 cubic foot, and it needs to cost less than $300. Right now, it's about 3 cubic feet, and it costs about $20,000. So we're trying to get there. Yes?
What is your first standard commercial product? What size? How many farads is the cap? And how many have you shipped?
Sergey, I'm going to have to let you answer that.
What Jim was talking about, this is technology which is now got seed investment to establish. Yeah, thank you very much.
It's on. Go ahead.
I can speak? Okay. So quick answer is the following. We're in the stage of building the manufacturing plant. But what the stage is now of this company that it has developed IP-protected proprietary technology and prototypes which were tested and performed these results. And now we're talking about what is the right business strategy to be, because there are different niches. There are very small, medium-sized, large ultracapacitors, and they have different niches and different markets. And each of these niches needs different model of ultracapacitor. Therefore, your question, it was not easy to answer from, let's say, from the Tribune, because it's necessary really to calculate what is the real need to be satisfied. That is the answer.
So when are you anticipating beginning volume production?
The first volume production, the first, let's say, manufacturing capacity that we are now building, it will be about 30,000 units per year, and it will be ready till the end of spring, next year. Why am I asking? Are you a potential client?
Well, I could ask the next question is how much a watt, how many dollars per watt or cents per watt do these cost?
You know, that's
you have to compete with batteries, where you always have the option, at least in stationary applications, of just buying more batteries to meet your power budget.
I would answer the following. If you have seen the already existing market for ultracapacitors, which are very expensive, it's already about $300 million. and it's growing annually not less than 30% during the last 3 years. What we possess is this technology which is at least 10 times cheaper if you compare costs, what will be the market price we are now thinking about. But it's cheaper and possess performance advantage compared to already existing at the market capacitors. Therefore, it can compete with for existing market as well. It can create the new demand from other potential clients which would buy it if it will be not so expensive as it is now. Is it correct, Jim?
Yes.
My statement?
Well, as he asked that question, this was the one slide that we actually took out of this presentation because we didn't think anybody would ask that question. So this is a slide that shows the current ultracapacitors and the APCT. The left-hand axis is dollars per watt hour, and the bottom axis is dollars per kilowatt. So you've got energy and on the Y and power on the X. So the dollars per watt hour are for the APCT technology about on the order of $20 per watt hour, whereas they're in the order of $10 per kilowatt from a power standpoint, versus competing technologies. If you just as an example go to the way right-hand side, the most energy efficient standard ultracapacitor on the market, where in the same power or energy level, dollars per watt hour, is much higher cost per watt hour. So that's, from our standpoint, from the APCT standpoint, this is the money slide for us. It's not the technology, but that's the money slide.
I would like, my name is Vladimir Biludit, I'm partner with Tech Invest, which has invested into this project. I would put it in a very simple way. We are not competing with any kind of batteries at all. What the batteries do, they provide power. What APCT, what power cap does, provide, not energy. APCT provides power. So it works together with battery. It does not compete with battery. Therefore, batteries are better for storing joules. Okay? APCT is great in providing watts. And they are not competing with each other. For your car, you have a big battery like 10 pounds or even 20 pounds because this battery needs to provide you with power. It has a lot more energy than your car requires. But you need to have such big battery because you need to have large surface to make sure your 300 amperes, which are used by your starter, are in place. If you have power capacitor, which is twice or even 4 times less in size than the battery, and the battery which is 4 to 2 times less in size, they will fit together and they will work like a power supply unit for the car. So we are not competing with batteries. We are talking different languages for the same reason.
You guys are out of time. So.
Yeah, we appreciate your attention, and we'll be here and answer any questions you have. Thanks for coming.